Good morning and welcome to our 10 o'clock press conference. Et tu Etna, new insights on classical eruptions of Etna, Vesuvius, and Santorini. And today we have Morgan King from the College of St. Benedict and St. John's University, Rafael Castro from the University of California at Berkeley, and Krista Evans from the University of Hawaii at Manoa. I'm going to turn it over to Morgan to start us off.
Is the laser pointer or?
So forward, back, laser pointer.
Okay, great, thank you. Hi everybody, thank you for being here. So I'm Dr. Morgan King, and I'll be talking to you a little bit about the historical perspective on this interdisciplinary project on the eruption of Etna in 44 BCE. So we're really interested in a series of years, 44 to 42 BCE, which were a pivotal moment in Roman history, in this sort of long, evolving process of the transition between the Republic and the Empire. And this time period also coincides with an underappreciated, abrupt, and dramatic climate change. Our hypothesis is that the cause of this climate change is an eruption at Etna in 44 BCE, which is attested to by many historical sources. In this project, we compare historical records, proxy records, and atmospheric models. I'm going to focus with you on the historical records. I work on Roman history and culture, so that's my area, but my colleague Rafael will go through the proxy records and atmospheric models in more detail with you. And we're looking, as we look at this evidence, we're looking at sort of two attributes. One, do the location of the changes make sense for an eruption at Etna, and does the time of the changes make sense? So I'll give a little bit more context on the history here. So the end of the Republic is an incredibly tumultuous and complicated period of history. We could look potentially at a 100-year process, which involves multiple civil wars. This political upheaval, we believe, has partly obscured a really major climate disaster. We've got a timeline for you here outlining just basically the last 15 years of the Republic. And you can see we've already got 3 civil wars, multiple famines. And the period that we're looking at here is 44, which coincides with both the assassination of Caesar and this eruption of Etna. Environment played a really important role in Roman life, as it does today, right? And we can think about this in 2 major ways. One, we can think about symbolism, right? That Romans actually are going to interpret events in the world around them as having political and sort of cultural, religious import. So we can think of omens, divine favor, disfavor, etc. There are also really practical effects of the environment and climate, right? Disastrous weather can impact trade and the ability to travel. Famine, public health can all cause riots and political unrest as well. So to hone in even a little bit more closely on these years, a guy by the name of Julius Caesar in the 50s and 40s was consolidating power in Rome. The sort of pinnacle of this is in the beginning of 44 BCE. He declares himself dictator for life of the Roman Republic, basically institutionalizing one-man rule. This turns out to be a shorter tenure than he probably anticipated, as a couple of months later, he's assassinated by a group of senators led by a man named Brutus. His death leads to a power vacuum that results in several years of civil war, and eventually the rise of his heir, a man named Augustus, as the first emperor of Rome. I say all of this to give some context and also to make the argument that this is a really important time period for Roman history, for world history, also for literature and art. Everything from Shakespeare's Julius Caesar to the more recent HBO's Rome depict this time period and its events. Okay, a little bit of geographical context. So the Roman Republic at this time was quite diffuse. It went all the way from Spain to modern-day Turkey, Egypt. Well, Egypt was not technically a province yet, but was already sort of incorporated in a lot of the structures. a lot of the agriculture, a lot of the food that's feeding all of these provinces is coming from the east, from Egypt especially, but also modern-day Turkey. Worth noting, so Etna is in Sicily, which is right in the middle of this territory, right at the heart, and very close to Italy, where we're going to see a lot of effects. And we have eyewitness records of a major eruption at Etna shortly before the assassination of Caesar in 44 BCE. And in the immediate aftermath of Caesar's assassination, we hear a lot about climate effects. Some of these are associated with Etna by Romans, and some of them are not. But they're all compatible with the effects of a major volcanic eruption. So the first major one that Romans talk about is darkened skies. So apparently the day after Caesar's assassinated, the sky turns dark and the sun is blotted out. There are also for several years cold winters. There are famines in Egypt and Greece. And there are also solar effects. So famously, when Caesar's heir Augustus returns to Rome, people see a halo around the sun. And that's what the image on the right, the image on the right here, you can sort of see actually, so they also call this effect sundogs, because you can see sort of the two suns on either side, but it's also actually from a halo. And this was seen as being very significant. So there are political and sort of social ramifications of these effects that we see in the record. Romans interpret them as having meaning. And you can imagine, if you lived in the time period and the person who's completely in charge of Rome at this time is assassinated and then the sky turns black, that's gonna feel meaningful, it's gonna feel apocalyptic. And it was interpreted as a sign of divine disfavor. Likewise, when Augustus comes into Rome, that solar halo is interpreted as a sign of divine favor for him. And it gets worked into the mythology of how he is meant to end up the first emperor, how he's meant to take control and set things right. Oftentimes, so we hear a lot about these environmental effects in the context of sort of prodigies and weird things that are happening in this time period that are interpreted in this political way, which I think has also contributed to them being somewhat overlooked. But our research and our project suggests that actually, these, far from being sort of just propaganda, that these are sort of natural human responses to some really substantial climate change that's happening at the time. So, ice core records show that one of the largest eruptions on record occurred in 44 BCE, and a major climate disaster lasting several years. You can see we've got this sort of scale here. So this would be what we have on the ice core records. So larger than anything that we've seen in the 20th century. One of the, I think, 3 largest that we have on record. So this raises the question, especially in the context of the ancient records of these environmental impacts. How did the environment change in 44 BCE? What are the impacts across the Mediterranean and even globally? And also, can we ascertain whether these changes might have been caused by this eruption at Mount Etna, which is so thoroughly recorded? And with that, I'll hand off to my colleague Raphael, who's going to present more of the science.
Cool. Thanks, Morgan. So, you've seen this picture before, but just to explain a little bit more. The white smoke is steam, and then the black smoke is ash, and you can see it being moved kind of like up and to the right, or up and to the left by the winds. And so that's pretty much what we're going to be looking at here. So a lot of those historical changes after the eruption are pretty similar to what we see after a modern day eruption. So if in this picture, we have a cartoon of Etna erupting, and you have a lower part of the atmosphere and an upper part of the atmosphere, and that's going to be relevant in a second. So the eruption releases sulfur aerosols, and those aerosols actually do a lot of different things. So once they're up in the air, they're actually blocking the sun, and that's going to cause some temperature drops, but that's also going to cause the skies to be darker, which is like what we saw in the historical accounts. It's going to cause those sundogs. It's going to cause those temperature drops. It's going to do some agricultural damage, mostly because of the sunlight not being able to make it to the crops. And it's going to cause some health and societal effects. So we saw the historical effects. There's also some health effects. They can cause like respiratory diseases, as we'll see in a second. And like I said in the picture, most of the location of these aerosols is going to be determined by the wind at that time. So what we actually did was try to just make a good guesstimate for where these winds would take these aerosols. And obviously we don't have satellite data for 44 BCE, but we do have pretty good climate reanalysis data from like 1948 to present. So what we did was basically just run this atmospheric model for all those years, from 1948 to 2018, and just get a probability of where these volcanic aerosols would go, and then compare it to our proxy records that we have to see if they agree with each other. So this is the picture that we saw earlier. We have in green on the bottom more modern eruptions that are smaller. Even these small eruptions are causing pretty big impacts. They do an 8% drop in crop yields, which is pretty huge. We have an intermediate eruption, which is, it caused 142,000 respiratory deaths, which is huge. And then there's this mystery point in 44 BC that we're trying to explore here, which is significantly larger. And so we're trying to explore this sulfur anomaly that we see from this ice core record. So we're going to look at other records to get a good sense of what's happening. We see a drop in temperature here from these two records. And then here we have a crop yield record. It is a record of China, and we'll see in the model later on that these effects do go as far as China, and that's why we're seeing a crop yield drop. And then there's also a coin hoard record, which will give us a good sense of civil unrest. I think this is a very interesting record. It's archaeological, and you can imagine that back in the day, banks were maybe less common. And so what are you going to do when the skies are turning dark and there's a bunch of stuff happening around you? You're just going to bury your coins, and then you die of respiratory disease because of the ash in the air, and your coins stay there for us to dig up 2,000 years later. And so we can plot all these records on a map and just see like where the effects would be spatially. And we see most of these effects happening in the mid-latitudes, and so we can compare our model. And so here we see that most of these effects do in fact happen in the mid-latitudes. Here the colors are going to be the height of the particles, and we're just going to, the eruption is happening on February 15th, and we're just going to run the model for a few days, 2 weeks, just to see where things are going to go. So the main thing we're looking for is to see if the eruption is actually going to cause effects in Rome, which is where the eyewitness accounts are. And so we're going to be looking for the lower particles to be in that area, which we do see. And then for the upper atmosphere particles, we're going to try to make sure that those actually do make it all the way up to Greenland, where we're going to see these ice core records. And we're also going to see that they go all the way to China to be able to cause these crop yield failures. And so just to kind of recap, we want to see that the fall of the Roman Republic coincides with these climate changes, which it does, as we saw in those timelines. We hypothesize that it's because of this eruption in Etna. And to try to further this hypothesis, we're going to compare historical records, which Morgan talked about. We compared proxy records, which is what we saw with the ice core records, with the coin hoards, crop yields, and the sulfur records. And we're also going to look at the atmospheric models, which is these particle dispersions that we're looking at that are from modern day climate reanalysis data, but we're going to use it as just like an idea of what might have happened back then. And so basically what it comes down to is we're going to look at the location of the changes and the time of the changes to make sure that those coincide, which they did to a decent degree. So that's all I have for you all. Thank you.
All right, thank you. Oh. So Now, moving on to the precursory activity and cultural response comparison of the late Bronze Age Santorini, Greece, and AD 79 Vesuvius Plinian eruptions. So, to give you a little background on the location, we have Santorini located in the southern Aegean Sea, approximately 120 kilometers north of Crete. Santorini is made of 5 islands: Theresia, Camini, Theresia, Esperanza, and Theresia are remnants of one larger island that was destroyed during the late Bronze Age. The reconstruction of this island is currently ongoing, so unfortunately I cannot show you that. Then about 1,500 kilometers east of Santorini, we have Vesuvius, located in the southern Campanian region of Italy. So to give a quick little timeline, we have the Santorini eruption, which was about 1650 BC. And the big thing to realize about this is that it is one of the largest eruptions that we've seen in the last 10,000 years. And I should also note that there have been no bodies found at the archaeological site of Precursory on Santorini. Then in AD 79, we have the Vesuvius eruption, which was a slightly smaller scale, and people were killed in place. So we have several different precursory activities that we use to determine volcanic eruptions, which is seismicity, ground deformation, and eruptions. So looking at Santorini earthquake history, between 1990 and 2019, approximately 79 earthquakes have been recorded. In 1956 was the last major earthquake that destroyed buildings on the island. And then we also have the archaeological record of Precursory that shows significant earthquake damage at the site. Then Vesuvius earthquake history, we have about 388 earthquakes that have been recorded between the years of 1985 and 2019. Luckily for this region though, we not only have the archaeological record, but we also have the written record. About 17 earthquakes have been recorded in the written record, with 4 of these also being seen in the archaeological record, including the AD 62 earthquake, which initiated the movement of magma and destroyed, had significant damage in both Pompeii and Herculaneum. So now let's move on to ground deformation, which we only see at Vesuvius. So it was used, the aqueduct system was used to model the ground deformation. As you can see with this blue line here, that is the original slope needed for the aqueduct system to have a proper fall. If there was any movement of the ground, this aqueduct system is going to break, and it is also seen at the archaeological site of Pompeii that this aqueduct system was being repaired at the time of the eruption. So now let's move on to volcanic eruptions, which we see at Santorini, but not precursory eruptions at Vesuvius. So at Santorini, there were 4 individual pulses of the precursory. This is very significant because the Therans on Santorini got away at this time. But then there was a short time gap that they came back and started sweeping everything up into a pile of debris. Then these people left again. So the big question is, where did these people go? Because there is no evidence of them moving into another island. There is no relic of Theran craft, Theran art, an influx of people at this time. So we know during the first phase of the Plinian eruption, it most likely created pumice rafts around the island. So they had gotten these boats and started paddling away in pumice rafts. So we have learned from Broodbank that they can paddle at about 1.7 kilometers per hour. Pause for dramatic effect. So after 8 hours, they have traveled 13.6 kilometers. This is assuming that they are paddling in pristine ocean conditions. So they are most likely not this far. So after 8 hours, this volcano, this eruption transitions into what we call phase 2, which is a series of pyroclastic density currents that are traveling in all different directions. Now, we know that pyroclastic density currents travel across water. We have seen this with the 1883 Krakatoa eruption, and we have most recently seen this with the 2019 Stromboli eruption. And using the information from the 1883 Krakatoa eruption, we can estimate that pyroclastic density currents can travel across the water at about 4.3 kilometers per minute. So after about 5 minutes, these people have been overwhelmed by pyroclastic density currents and have most likely been killed at sea. So again, we use earthquakes, deformation, ground deformation, and precursory eruptions in order to determine impending volcanic eruptions. While looking at Vesuvius and Santorini, the responses to these eruptions have been various. Whereas at Pompeii and Herculaneum, you see people trying to escape or trying to wait out the eruption and were killed. And at Akrotiri, these people abandoned the island, returned, and then abandoned the island again, but were most likely overwhelmed by the pyroclastic density currents at sea.
All right, thank you, Krista. I'm going to open the floor to questions from reporters in the audience.
Hi, Tom Garland House, freelance. I wonder if you could give us an idea of sort of the scale of the magnitude of the Etna eruption. I know you said it was sort of on a scale that we haven't seen historically, but is there any type of template, current template, like it was for Mount St. Helens or something like that?
Okay, I mean, we don't know like for sure exactly how big it is. The thing we're looking at that looks really massive is the sulfur spike. And so specifically for Etna, like the tougher deposits weren't that much, right? So, you know, from the deposits that you would see from an eruption, you would imagine that it was like a relatively small eruption, but Etna is pretty gassy. And so like in that picture that I showed where there was gas coming out of the eruption, you see steam and you see ash, but what you don't see is like the carbon dioxide and the sulfur coming out of the eruption. That's just invisible gases that are going to travel up. And so it could have released a lot of sulfur, and you wouldn't really see that. So when I say like a big eruption, it wouldn't necessarily look huge and spectacular. It would just release a lot of sulfur like continuously. And that's that big spike that we're seeing that causes all these effects.
Thank you.
Mm-hmm.
Do you have other questions?
The Christoph Seidler, Der Spiegel, that's on Etna again. Have the results been published, or how does that work?
The results have not been published yet, but I think will be soon. We're
you have other questions from the audience?
Horst Rademacher from Frankfurter Allgemeine Zeitung in Germany. Just a question about the precision of the dating of the sulfur spike in the Greenland record. I mean, you put it, I think you even put a date on it, 15 February or something like that. So how precise is that?
So the 15th February that we have is actually from the historical accounts. We don't know that the eruption happened right on February 15th, but actually, can I show a slide?
Sure.
So, I mean, we don't know if like a super high precision. Plus or minus a year, you said? Okay, so that the ice core is plus or minus a year. And then for February, like I said, it's the historical accounts.
Within a year.
Yeah, plus or minus a year. So, you know, it's not like we can't necessarily say it was 44, but we can say it's somewhere around there. And then for February, what we did was we ran the model for different months just to see where the scattering would go. And February was actually the month that agreed the most with where the records were, as you can see here. So this is just a distribution of where the particles would go. And you see this one going like off to the right and a lot in Europe, which is where the crop yield failures were. So that was the main reason we kind of put the timeline together, but it's still some uncertainty there.
Hi, I'm Tushar, who is part of the study. So I would also add that so there is about a plus minus 1 year uncertainty in the ice core records, but with variety of other records which show a large temperature signal that you should expect to see for that much sulfur release, because it's about 5 to 10 times the size of Krakatoa in 1883. If you start combining all those records, then you get a little bit more precision because they have different uncertainties. So that helps pin it down more closer to being in 44 BC time period. So the ice cores themselves have about plus minus 1 year of uncertainty. But when we start comparing the ice core records with the variety of other proxy records, a couple which Raphael showed, but we looked at a variety of other ones, they have their own uncertainty, but you can start to look at what is the likelihood that they all slightly offset and have different causes versus being around at the same time. So that gives a little bit more precision to suggest that it was 44 BC. But there are uncertainties with all the aging methods of about a year in general.
Do we have any more questions from the audience?
I'm curious about what historical records you consulted, because the fall of the Roman Empire, I think, was a pretty complex process that played out over a very long time.
Yeah.
So I wanted you to sort of clarify what you mean by that. You know, what are the evidence of damage to the empire that coincide with this event? I'm just trying to clarify that a bit.
Yes, and you know, we do want to be clear. The fall of the Republic is an incredibly complex time period, and you probably first have to look at political, military, economic causes for that. So we do not want to say that overstate this, but that there is clear evidence of a climactic disaster in this time period. And that's probably a factor that we haven't been looking at closely enough. And that, in fact, our sources actually do reflect concern over climactic change and are interpreting it. And so we do have, we have evidence from contemporary poets. Virgil, Tibullus both write about it. But we also have some ancient historians, Livy, Plutarch, Suetonius, also all talk about it, and there are others. If you email me directly, I can give you more citations, but we are seeing it in a variety of written sources as well as some of the archaeological evidence.
So is the coin hoard record new? There is a citation. Okay. Thank you.
Do we have any more questions from reporters in the room? Anyone on chat? Nope. All right, well, I'd like to thank our panelists. And that is all until 11. We will resume with the Arctic report card. Thank you all.